We need to describe and explain the process of phase change in terms of a molecular behavior on a microscopic scale, and why temperature doesn't change during a phase change. Distinguish between evaporation and boiling, define specific latent heat, and solve problems. Okay, so first things first. Remember that we've been talking about specific heat, which tells us how much the temperature of an object changes when we add heat to it. And every type of material has its own specific heat. So by adding heat, usually you will have a temperature change, and that will be determined by the specific heat of the material and by how much of that material you have. So mass and specific heat determine how much temperature changes. When something reaches a boiling point, okay, or a melting point, what we call the phase change, where it goes from a solid to a liquid or a liquid to a gas, if I'm adding heat to it, it no longer changes temperature. That energy that I'm giving it is no longer going to increase the kinetic energy of the molecules. Instead, what it's doing is it's changing their potential energy. It's giving them energy to move apart from one another. And since all that energy is going to break those bonds, then what happens is the temperature no longer changes, okay? So the energy, it's easiest to imagine, it goes both ways, but it's easiest to imagine it one way. If I'm heating something up, I have a block of ice. As I heat it up, as I add energy to it, it gets warmer and warmer and warmer. When that ice starts to melt, remember, temperature is a measure of the kinetic energy of the molecules. When that ice starts to melt, the kinetic energy is no longer changing because it takes energy to melt the ice, to turn it from solid to liquid. It takes energy to get those molecules farther apart. So the temperature at that point stays constant until the ice is completely melted, and then the temperature of the water will start to rise. Okay.
So it takes energy.
So let's look at what a graph of it looks like then. Okay. Let's show you a picture of it here. Boom. Now imagine this as being a big chunk of ice that originally started at negative 40 degrees Celsius. The y-axis is degrees Celsius. The x-axis here is heat added, but you can just think of it as like, it can be heat added, but it can also be time if I'm adding heat at a constant rate, okay? So the first thing that happens is I'm adding heat and my ice warms up to 0 degrees, and it does so linearly, okay? But when it hits 0 degrees, it begins to melt. And now the energy that I'm giving it is no longer warming it up. Instead, it's going into melting the ice, to breaking down those attractions. And so while it's melting, I'll end up with an ice-water mixture that stays at 0 degrees Celsius. Even if I have it on a flame and I'm adding heat, as long as that ice is melting and it's being stirred, it'll stay at 0 degrees. Once all the ice is melted, that's at this point right here, okay, all the ice is melted, then the temperature of the water will start to increase, all right, because I'm no longer changing phase. And it'll do that all the way up to 100 degrees Celsius, and if I'm at sea level, and then it doesn't get any hotter. The water does not get hotter because now all the energy is going to turn that water into steam. And that water will stay at 100 degrees until it's all evaporated, and then my energy will start heating up the steam more, and the steam will get hotter and hotter and hotter. Okay? A couple things to notice, and then I'll get your question. Notice that what we've been talking about is this stuff, Q equals mc delta T. I can figure out temperature change and when I'm in a particular phase very easily using mc delta T. But notice that the slope of this line and this line and this line are not the same. Why is that? Different specific heats. Ice, water, and steam have different specific heats. And therefore, if I add heat continually, they will change temperature at different rates because their specific heats are different. I don't know why the water and ice are more similar, but let's look at the slopes for a second. Let's look at the slope of the ice versus the water versus the steam. Looking at the slopes of those, can you tell which one has the greatest specific heat? No. Steam, ice, or water? Water. Water does, because it has the least, the most gradual slope, right? Which means if I'm adding heat to it, its temperature is changing most slowly. Therefore, it has the greatest specific heat. Yeah? That's a real common multiple choice question on IB exam. Look at this graph. Which one has? Okay. So what would be really helpful to us now, since we can now calculate, we know how to calculate energy in terms of changing temperature for a particular phase, what would also be really helpful is to figure out how much energy it takes to melt something or to boil something and turn it into vapor. And it's very, very easy. The math that we do now is Q equals the mass of the stuff that I'm trying to change the phase of times this new quantity that we call the latent heat. And there's two different kinds of latent heat. There's latent heat of fusion and latent heat of vaporization. Going from solid to liquid is the latent heat of fusion. Going from liquid to gas is latent heat of vaporization. Okay, so in this case, it would be latent heat of vaporization. So what I just told you, I'm going to say on this slide. Latent heat. Latent heat of fusion is the amount of heat that's required to turn 1 kilogram of that material from a solid to a liquid. And the latent heat of vaporization is how much heat is required to turn 1 kilogram of that particular material from a liquid to a gas. This is either how much heat is absorbed to do it one way or how much heat would be released if it went the other way. And to find out how much energy is absorbed or released in a phase change, you just take the mass of the material that's being changed times the latent heat of fusion if we're going from solid to liquid, or vaporization if we're going from liquid to gas. Okay, so let's think about this just real quick. Okay, you got a big freeze coming on. You just got all your apples on the tree. You haven't harvested them yet, and it's like, oh man, big freeze is coming. So one of the things farmers will do is they'll spray water on their fruit plants and their fruit trees to help save the fruit. Why would it do that? What's going to happen? What do you think? So something to think about. Let's think about this on a microscopic level now. We talk about evaporation being a cooling process. Heat needs to be absorbed in order to make something go from a liquid to a gas. But let's think of it on a molecular level. If I have a pot of water and some evaporation takes place, the remaining water will be colder. And we talk about heat being absorbed, but let's think about what's going on with the molecules. Which molecules will be the ones to evaporate first? Okay. The ones with the highest kinetic energy, right? They're going to have enough energy to go ping and go flying off and turn into a gas. So what do you have left? And therefore, you have colder water, okay? So that's another reason why things cool when evaporation is taking place, okay? Something to think about there, and we're going to stop here, and I have 5 minutes to explain one more thing to you quickly.